Okay, off we go. Welcome back. Don't forget about the attendance quiz, attendance code, all that business. And we're going to pick up where we left off last time. Just a reminder. Now, hopefully everybody's clear enough on what the class schedule says, but what we're doing today is actually not fair game for the midterm, right? And that's just kind of the way things have to work. I mean, my alternative would be to make it fair game for the midterm. I don't think anybody wants that. So anyway, a little bit weird that we're going to spend the day before the midterm doing stuff now in the midterm, but that's, again, the least bad of our reasonable options. Okay, so last time we entertained this question. What if your domain is what I like to call dimensionally awkward? Right? So it's got a different dimension than the world that it lives in. And none of our existing Riemann sums really work with that, so we had to make a new idea of a Riemann sum. And it's strategically the same as every other Riemann sum we've written down. Take your domain, whatever it is, however weird, whatever problems it has, chop it up into little pieces. Right? And then argue that on each little piece, the problem turns into an easy problem, and it's the way I like to think of these is quantity per unit size times size, which I like to think of even more sort of streamlined as density times size. It's always some sort of a density, suitably interpreted. Always some sort of a stuff per unit size, that's a density. So density times size. And then we notice that, again, structurally and strategically, this is a lot like every other integral we've written down. And so we kind of copycat our notational patterns. And I think the term line integral is pretty reasonable. I mean, some people call it a path integral. I've never heard it called a curve integral, but that would make sense too. And I like to make the point specifically, and Kali does as well, to call this a scalar line integral. Scalar line integral, because the integrand is a scalar. Seems silly to say so, but also the differential is a scalar, and this is going to be in contrast to another kind of integral we're going to see later today. So anyway, scalar line integral. Excuse me. We talked about how to compute it. Again, we're kind of stealing from past work. When you have a domain that you don't like, view it as being an image. In this case, viewing a curve as being an image of something, old news. That was the whole idea of a parameterization. And you may recall, or maybe you don't, but back when we were talking about parameterizations a lot back in Chapter 1, I made the observation it's going to be a big deal when we get to Chapters 6 and 7, and here we are. Okay. All right, so details to talk through, and we have our nice pullback formula. Note that this results in a good old-fashioned single variable integral. Right? Integral from A to B. Single variable dt. Right? Everything in here is a function of t. It's the Calc 1 style single variable integral. And so basically the big idea is pull back through the parameterization. Don't forget to insert your stretching factor. That's all there is to it. Okay. And we did several examples last time. There's sort of several examples all with the same sort of setup. There, same curve, same parameterization, et cetera, et cetera. Okay, so that's where we're going to pick up. Another example. This is kind of a different sort of idea. Yeah, there we go, full screen. So suppose we have a fence sitting on the unit circle, and here's a part of that unit circle. Here's sort of the whole unit circle. You can see we're eventually going to parameterize that. But anyway, sitting on top of the unit circle, we have a fence, sort of like this. And you could imagine that as the circle goes around, the fence kind of goes around as well. And why do we have a circular fence? To make it interesting, I suppose. But anyway, that's what we're looking at. Okay, so let's talk about how we would compute the total area. I think it's a reasonable pitch that the total area, if I want to add up if I want to take the total of all that area, then I should look at each individual, I'm going to call it a picket, right? If I just add up all of those pickets, whoops, wrong color, over the entire curve, right, adding up over the entire curve, that should give me the total area. What do you think? Does that make sense? Okay, so now let's look at those individual pieces. Okay, so that individual little piece there, that area, well, it's a little rectangle, or at least close enough. And we can talk about the height of that rectangle. Well, that height is given. There it is. And let's see here, the, what do we call, I guess, the width. That width is a little piece of this curve. And reminder, when we're making a scalar line integral, that's what ds represents. ds, sort of a notational shorthand to represent the delta s, that represents how long is a little piece of that curve. Right. So that's exactly what we're looking at here. There we go. ds. And sure enough, dA, I can, highlighter mode. dA, I can think of as height times width. What do you think? Does everybody see how that developed? All right, so now I started with sort of a geometry problem application, and what we've ended up with, I've talked about how to rewrite that as literally, explicitly a scalar line integral. So now, before us is just the task of computing this scalar line integral. We're going to use the formula from the previous page. Well, excuse me, from 2 pages. We're going to parameterize. Right? Then we're going to write down our stretching factor to insert. And then other than that, it's a matter of plugging in, pull back through the parameterization. Okay, so here we go. How do we parameterize our unit circle? Well, old news. We know how to parameterize the unit circle. That was, in fact, I think the very first parameterization we ever wrote down. Right? And we got other options. You could do it different ways if you want, but this is going to work just fine. Let's see. Per the formula, I need to take the derivative. I need to then take the magnitude of that derivative. That gives me my stretching factor. Don't forget to insert that stretching factor. Is that cool? Everybody with me? All right, and let's see, the thing that remains then, when I say insert the stretching factor, another way to say that, of course, is that ds is stretching factor times dt. Okay, so now we do also have to insert, rewrite, pull back, h being our height as a function of position. So we have that formula, x plus 2 over 5. Okay, so so we insert that. And all that remains now is to figure out what to do with that x. Right? And it is easy to lose track. It's easy to forget. Wait a minute, x is, what's the formula for, how do I know the formula for x? Remind yourself, the parameterization literally, explicitly gives x and y as functions of t. Whatever you are pulling back through, change of variables function, parameterization, whatever you are pulling back through, that's what gives you those formulas. So x, you see right there is the first output of my parameterization. That x is cosine t. How are we doing? Is everybody happy? Is everybody okay with this? It's very plug and chug. You gotta kind of love it in some sense. It's just, you gotta make sure you know what's going on, what these objects are, and then this formula does all the work for us. Okay. Oh gosh, excuse me. So let's do, I'm going to say another example. This next example, we're going to go into this optimistic, hopeful that this will be another nice example of how I can use a scalar line integral to solve a problem. It's going to seem like it will. And then we're going to find partway through that something's up, something's different, and this is really better thought of as a different kind of a thing. So here we go. Excuse me. Let's return to the discussion of work. Y'all may recall we talked about work back, again, chapter 1, going way back. The high school take on work is that it's force times distance, both being thought of as scalars. We made the realization back in chapter 1 that that's just fundamentally misguided. Force has a direction. It's not a scalar, it's a vector. Displacement has a direction. It's fundamentally a vector, not a scalar. So reinterpreted as vectors, this is what we ended up with. And nice discussion how the properties of dot product dovetail perfectly with the sort of the asterisks of high school discussions of work. Okay. All right, now that said, this improved, better take on how to compute work is also flawed. This assumes that your force is constant. In the real world, usually isn't. Right? This also assumes that your displacement is over a straight line path. In the real world, it usually isn't. Right? So, what are we going to do? How are we going to entertain? We can't use this formula. But what if the force is not constant? And what if the displacement is not over a straight line path? So what if we have instead, what if we have a path that's all curvy and stuff? Like so. And what if our force is non-constant? Notice that what I've got here, very much not constant. Cool, you see the question? Right now, I have a favorite personal metaphor for this. In other words, how do I visualize? What do I imagine going on here? I like to think of this as a windy mountain road, and I like to think of the force as being the amount of force that I have to exert to keep from rolling downhill. Right. So if you're standing on a inclined surface, gravity is pulling you, and you have to apply some sort of a force. Sometimes it's just with your toes, right? But you have to apply some sort of a force to keep yourself from rolling downhill. So these blue vectors are the force that you're exerting to not fall downhill. That's my metaphor, right? Now, there's different. Take whatever metaphor you like, whatever. This is the one I like personally. Okay, so the big strategy here is I'm kind of proceeding naively in the hopes that I can just do a scalar line integral, and let's take our curve and chop it up into little pieces. And on each little piece, well, conveniently, this non-straight path, well, on that little piece, it's pretty close to straight. And I have a non-constant vector field, but on that little bitty piece that I don't move very far, the force is approximately constant. So on that little piece, I feel like a hard problem has turned into an easy problem. I'm still feeling pretty good about this. Everybody with me? Okay. All right, here's where things get a little weird. I have to recognize that if I want to compute work, I have to distinguish between going up the mountain road, uphill, versus maybe instead going down the mountain road. These would be very, very different experiences, right? So, the direction matters. That was not the case when we were talking about fences, right? Which direction does this fence go? Does it matter in terms of the area whether I think of this as a clockwise fence or a counterclockwise fence? What does that even mean? And no, it doesn't matter, by the way, so who cares what it means? right? It doesn't matter. Likewise with, if you're computing mass, for example, there is no sort of notion of which direction the mass, it just sits there, right? So something is already pretty different. There, we have to decide on what we call an orientation. And an orientation is just a choice between these two options. An orientation says at any given point, there needs to be a well-defined choice of which way are you going at that point. And that choice has to be consistent across the entire curve. We have a different kind of a domain than we had in all of our previous examples. This is not just a path. This is an oriented path. Does that make sense? And it's actually kind of worse than that. Because it's not just that I have to choose between two things, it's that at any given point, the fact that the path is kind of like this, as opposed to this. Right? I mean, it makes a difference, right? I mean, how hard is it to go some small amount that direction? Well, that might be maybe not so uphill, but if I would say I want to go this direction, well, that's pretty uphill there. And it might well be that it's harder, more work to go in that direction than that direction. So it's not just a choice between two different directions on the path, it's how the path is arranged in space will affect how much work happens on that little piece. This is not how fences work, right? If you have a fence picket, and if fence picket is sitting like this, kind of like my hand is here, has a certain amount of area. If I were to turn that picket to the side, same amount of area. How that picket sits in space got nothing to do with anything, right? But with work, it does. So this is a qualitatively different kind of a question. Everybody see what I'm talking about there? And so it remains to be seen whether we even can deal with this with a scalar line integral, or even anything that we might be willing to call a scalar line integral. And I'm going to say it a little bit differently. Whether we can or cannot do it with a scalar line integral, I would propose, hey, when you have a fundamentally different type of question, let's not try to fit that square peg into a round hole. Let's just view this as being a different kind of question. And let's see what would be the natural way to write down how to answer this question as it is, and see what happens. Okay, so good news, it works out really nicely and simply. It's arguably even easier than a scalar line integral. Here's the little piece of curve. Some individual little piece of curve, and I'm going to ask how much work does it take to move along that little piece of curve? Well, as we've arranged it, moving along that piece of curve, I can approximate my displacement, dr, and I can approximate the force that I have to apply across that displacement. And we've made the case that this is approximately a straight line path. The force is approximately constant, and work is force dot displacement. So boom, dW is F dot dr. And we can just add those up. dW, F dot dr, adding up over the entire curve, and we get this expression right there. And notice, it does not look like a scalar line integral. Everybody okay? Everybody happy with that? Okay. So, look, I still kind of want to call this a line integral because it's still an integral that's happening over a curve. So I think line integral, just for the sake of consistency, that makes sense. But check it out. This is pretty weird. We have a vector integrand, and even weirder, we have a vector differential. We have never seen a vector differential in this class previously. But again, it kind of makes sense here. I mean, that's this vector differential, this dr vector, is literally the displacement that I need to know which direction that points matters, right? As part of computing how much work happens on that piece of curve. Everybody happy? All right. So yeah, new kind of line integral, vector line integral. How to compute such a thing? Good news. We actually already have all the tools we need. We just have to kind of make the observations. So I am going to do a callback. So everything that I have in the purple there is a flashback to section 3.2, as I recall, at the very top of section 3.2, in my notes in section 3.2. And various players involved in parameterizations of curves. And please do go back either in the book or in my notes, whatever, however you prefer to do it, and remind yourself of these various objects and these various relationships we have between them. These are going to be a big deal throughout all of Chapter 6, so you want to make sure to be fully up to speed, polished, and fresh on all of that. And then, with that in mind, this construction, our new vector line integral, I can rewrite it in several different ways, just rewriting the dr. All these different ways that I know to rewrite dr give me effectively different notations for vector line integrals. And they all have their sort of merits, pros and cons. And we're going to talk about all of these. We're going to focus on the first two today, but we will get to the third one as well. Okay. All right. So in particular, let's talk about what we're going to do today. This is my favorite notation for representing vector line integrals. You might even be able to guess why I like this. I mean, among other things, check it out. It's the shortest one. It's the fewest pen strokes, right? It's the easiest one to write down. That's got to count for something. But I also like it for kind of what I'm going to call philosophical reasons. So in particular, this dr encodes everything that you need to know about your little bitty piece of curve. That little bitty piece of curve, I'm going to need to know how long it is. The magnitude of dr tells you how long it is. I'm going to need to know how that points in space and which direction I'm going along that little piece of curve and how it sits in space. That is encoded in dr also. Everything that you need to know about that little piece of the domain is written in dr. And I think there's something kind of neat and tidy about that, which I think is appealing. And then I'll point out further what we would call the integrand here, f. Everything in f is what you might call external to the curve. It's telling you about forces that you have to apply as you're moving along the curve, but they're not intrinsic to the curve itself. Does that make sense to everybody? It's kind of like a sort of it's just an organizational point, but I think that's nice. Now let's talk about this next form. Why do I like this form? Well, I like this one because this is plug and chug. Right? This, again, check it out. It's a dt integral from a to b. Everything here can be rewritten in terms of t. It's very plug and chug. And in many situations, of course, being able to compute something, being able to turn the crank and see what the actual answer is, we've got to determine the numerical value. We need plug and chug formulas, and this is it. So that's nice as well. Okay, real quick, last thing. I'm going to kind of trash talk a little bit about this one. It does have its moments. I like it in certain ways. Here's what I don't like about it. There have been several instances this semester where I've talked about how, look, if you have two things that are different, let's not conflate them. If they're different, it's important that they're different. we should use different terms to refer to them, right? So that's my little soapbox speech about orthogonal versus perpendicular, for example. These are different concepts. We need different words for them. So I don't like conflating things that are different. And let's face it, this is a different construction. This has got, orientation is a big deal here. It was not for scalar line integrals. I think this is a importantly different thing from a scalar line integral, and yet this notation kind of makes it look like we're talking about a scalar line integral. That's unfortunate in my book, right? I think when things are different, they should look different in how we represent them. So anyway, my little gripe. Okay. All right, so let's do one. Let's see here. We have a curve here. Top half of the unit circle, oriented counterclockwise. Now, reminder, before we go on, our domain is no longer just a curve. Our domain needs to be an oriented curve. You've got to tell me which direction we're going on the curve in question. Uphill is not the same as downhill, right? So orientation matters. So that being said, specifically the orientation here, counterclockwise. So there's our curve, and then as we move along that curve, there's a force involved here. Let's see. It says here that the wind is exerting a force on you, as described by that vector field. So we've got a force, we've got a curve, vector line integral. Seems like we would just kind of write it down and plug it in, etc. There's a little subtlety here. This is a bother. I'm sorry. This is an annoyance. The real world can be super annoying sometimes. If I have a mass of some sort, unless I'm holding this stylus with my hand, there are actually two forces involved, right? If you've had an intro physics class, I'm sure you know this. Gravity is pulling downward. I am pushing upward. These forces are what we call equal and opposite, right? Equal magnitude, opposite direction. Which one of them matters depends on the context. Right? So in this context, the question says, how much work do you have to exert, right? It says you're the one whose work we want to measure. So the force that you are applying is what we're interested in. The vector field tells me the force that the wind is applying. Right? The wind is blowing this way at me. I have to push the other way to oppose it. That makes sense to everybody? Okay, so again, we are given F, but the force that we're interested in is negative F, because the work we're interested in is the work that we're doing. Everybody okay with that? That minus sign is important. It's one of these little micro annoyances. It's conceptually, you just have to kind of think it through. But you got to get that part right, because if you get it wrong, you get a wrong answer and your bridge falls down. So important but silly little detail. Okay. All right. Okay. Now it's plug and chug. Step one, we got to parameterize our curve. We're interested in the unit circle. That's how we parameterize the unit circle. Let's be careful, though. We are only interested in the top half of the unit circle. So t goes from 0 to pi only. That gets us just the top half. We know we're going to need r prime, so we take the derivative. Let's see, I'll do it like this. We take the derivative there. Easy calculus. And then it's plugging in. Everything here is just a matter of plugging in. Let's see here. This is what we derived on the previous page. The vector field F was given as that. We know that dr is r prime dt. we just computed our prime. Let's see here. T goes from 0 to pi, so our bounds 0 to pi. Everybody with me? And here again, we have this question that keeps popping up. Okay, but what do I do with this whole x and y thing? X and y, or I need everything in terms of t. Always, whatever you're pulling back through, that tells you how to plug in. And so, let me clear off all of that. You want to know what x is? What do I do with that x right there? Okay, well, it's the first output of my parameterization. So x is cosine t. Everybody happy? There's several minus signs in here. Do be careful with these various minus signs. You got the minus sign from the, wind is pushing me, I'm pushing back consideration. And then there's this minus sign that comes from the vector field, and it is surprisingly easy when there's multiple minus signs running around to whoopsie one of those minus signs. So please do be careful with that. You'll notice I left them all explicitly in here throughout until the very end of everything being plugged in, so that I'm less likely to forget one or inadvertently cancel 3 of them, or who knows, right? So anyways, be careful. Okay, we get an easy single variable integral. Works out very nicely. Okay, everybody good? Okay, y'all will recall when we first wrote down scalar line integrals, and we did the pullback formula for scalar line integrals. I made the observation that the parameterization, that a little bit scary to see that parameterization showing up as if it matters when it shouldn't matter. A little bit scary, but conveniently the parameterization doesn't matter. Go crazy, do whatever you want. I mean, you regularity, it's got to be continuously differentiable, whatever. Okay, so do we get lucky again? Notice that our new formula, where did it go? Our new formula, again, the parameterization shows up in the formula as if it matters, but it shouldn't matter. Does it matter? We got to worry about that. And there's a little bit of a subtlety here. It's tempting to say that it doesn't matter, but it kind of does. It's got to have the correct orientation. Remember, we're not just parameterizing a curve. The domain, when you're talking about a vector line integral, your domain is not just a curve. It's an oriented curve. And your parameterization, it has to follow the actual curve, and it's got to go with the actual orientation. So the parameterization matters. You've got to go the correct direction. Otherwise, you're not going to get the right answer. Now, the good news is, if you go the wrong direction, and this is easy to see in the picture here, if you go the wrong direction, then instead of your dr being like so, if you go the wrong direction, your dr is just going to be pointing exactly the opposite direction. And these are different, but they're conveniently different. They differ by, in some sense, very little. They differ only by a minus sign. They differ by exactly a minus sign. So knowing that we're off by exactly a minus sign in every single term means that I can conclude that about the integral as a whole. If you parameterize the wrong direction, you will be off exactly by a minus sign. And that's the punchline of what I've got written here in this definition and theorem. This is a lovely notation. A superscript minus sign just means go the opposite direction, orient the wrong way, the opposite way. And the theorem just points out that when you're looking at an integral over a curve, if you go the wrong direction, that will give you a wrong answer to the tune of, again, exactly a minus sign. That make sense to everybody? Everybody happy? All right. Okay, so there's a couple of ways to think about this. One way to think about this is get it right. You don't want to get it wrong. That's not really the best way to think about it. What I would suggest we think about this is, okay, so I can choose to orient the wrong way as long as I understand that that's just going to create a minus sign that shouldn't be there, and I can account for that by just introducing the appropriate additional minus sign. Right? So this is not a measure. It's not just a measurement of how wrong you're going to be. This is telling you the low cost that you have to pay if you orient the wrong direction, and you're perfectly welcome to just pay that cost, and there's no problem. Okay, all right. Now I've got an example here. I'm going to show you 4 different ways to answer this question. They're all worth talking about. I was going to say they're all good, but they're not. The 4th one I'm going to show you is a bad answer that you should not do, but we'll get to that. We'll get to that last. So we're going to consider the same question we looked at previously. It's just that now we're going to say we're going clockwise instead of counterclockwise. Now, oh my gosh, how are we going to deal with this? We've got to parameterize a clockwise circle. I'm going to show you 2 different techniques, 2 different ways of thinking about this. I think both of these are good. If you want to go clockwise, how about you just define t in your picture like so? Now let's think about what that would mean. Notice this t is not theta. Right? Very often, just kind of for convenience, we let t be theta, and we're always going counterclockwise. Here, different, very importantly different. Here, t, not theta. But I'm allowed to set up my parameter any way I want to, and if I do it like this, when t equals 0, I'm here. And then as t increases, I move clockwise, as I'm supposed to. And then when I get to the end, I know exactly what t is at the end. That's where this angle t would be pi. So that's one way to do it. And once you set up your parameter like that, you just have a little bit of a geometry problem to figure out, okay, well, how do I describe position then? And the best way I think to see position is to note that if that's t, then this is pi minus t. And that, by the way, is theta. And position is cosine theta comma sine theta. And then, by the way, just a reminder, I need everybody to know the angle addition formulas for sine and cosine. They're super useful. Despite you might not have been required to know those in a high school trig class. Maybe you did, maybe you didn't. I'm going to need you to know them. So make sure you know angle addition formulas, and with those you can rewrite this as that. So I'll say make sure that you can make this, make sure you can do this right here. It'd be a good exercise to make sure you just do that final simplification. Okay, here's a different way to do it. Same clockwise parameterization. Let's recall that this thing that I'm looking for, not the same as the counterclockwise one we just talked about, and which we of course know and have known for a long time, but even though those are not the same, they relate in a very convenient way. These are pretty clearly reflections of each other over the y-axis. Right, so again, picture, you give me this point in the clockwise parameterization, and it is literally the reflection of this corresponding point in the counterclockwise parameterization. And so, well, what do I do about this? Well, reflecting, you can see it right here in the picture. That reflection will just give you a minus sign on the x coordinate. And check it out, we get the same answer we got on the other side here. Everybody good? All right, so that's two ways to solve the problem. Both deriving the same parameterization, and again, once you have the parameterization, then it's, off you go. Plug in, pull back, same kind of stuff. Okay, here's by far the best way to do it, though. Best way to do it is just make the observation. Yeah, I already did the counterclockwise one. I already know that counterclockwise gives me pi. I have been asked to now go clockwise. Clockwise is just the same thing with the opposite orientation, and opposite orientation just gives me a minus sign, and therefore minus pi. So much easier. You don't have to reparameterize. We're just capitalizing on this trick that we talked about here. Yes, this theorem tells you you'll get the wrong answer if you parameterize the wrong way, but it also tells you exactly how wrong and exactly what way, and again, you just pay the price. Just throw in that minus sign and acknowledgement that you went the wrong way. Perfectly reasonable, and I think, again, really the best answer of all three of these that I've shown you so far. What do you think? You like that one? Everybody happy with that? Okay. All right, now here's the fourth one. I don't care for the following. I think it is there's a lot of problems. It's going to be alluring. You're going to feel the urge to do the following. Please resist the following urge. I think it is mathematically, in the context of Math219, this would be a problem. And that is what I like to call the time travel argument. Where we say, let's just think of time going from pi to 0 instead of 0 to pi. I mean, look, counterclockwise, there's 0, there's pi. If you want to go clockwise, we just go from pi to 0. Why don't I just write down pi to 0 and be done with it? Everybody see the urge, right? I mean, that seems reasonable, doesn't it? Well, couple of problems with this. First of all, the arguments that we've been making about how to handle these kinds of integrals involve thinking of t as time. We have good intuition for the passage of time, at least in the positive direction, and I question whether we really do have acceptably solid intuition for what happens when time goes backwards. I don't think we really have that. So, I don't really get the suggestion here in that sense, right? And so you may be thinking, all right, but whatever. I mean, who cares? I mean, look, this is clearly going to give us a minus sign. It is the same minus sign that we would have gotten by this. So what's the difference? And let me remind you, the big difference is one of them we argued by a perfectly mathematically valid, reasonable argument. And the other showed up because of a science fiction argument. Right? So, it's not a good argument. It's not about the answer. The fact that this would give you the right answer is not the point. Right? The point is, as an argument, I don't see what you're claiming to understand here. It's a problem. Right? And now, just to emphasize the awkwardness, my claim that you don't have a good intuition for time running backwards, well, here are some formulas that are on the table and in play when we developed the framework that we have for answering these questions. Here's the thing. If you're claiming time is moving backwards, time is moving from pi to 0, these are both wrong. It's straight up not true. For example, if you don't change the parameterization, right, if you use the old parameterization, r prime does not change. It's the same r prime. You didn't change it, it's the same. But your velocity did change. Your velocity is literally the other direction now. Right? That's a problem. So these are now no longer equal to each other. So this argument that a student doing this time travel argument, the argument that the student is making is based on a development of a framework using equations that aren't true anymore. Not cool, right? Does everybody see that? That's really a problem, right? So please don't make these time travel arguments. At best, they are unclear. And I suppose you could, fill in the gaps, but why would you want to do that? There's nothing to be gained here. I got to point out, there's no reason to want to flesh that out when we could just do this in the first place. Plenty appropriate mathematically. Much easier than trying to flesh out time travel arguments. So anyway, heads up on that. Please be careful with that kind of thing. Please be reminded that it is the argument that we are the most interested in. It's the argument, the quality of the argument that determines how it's graded. Right? So it's just that's just a bad road to go down. Okay. Last thing, and we're not going to finish this page and a half discussion that's about to follow. But the next natural thing to ask is, okay, so if we have this vector line integral construction, we know how to interpret it when the integrand is a force. The integrand is a force. This represents work. Cool. What if that vector field does not represent force? What if the vector field represents a fluid flow? What if it represents, let's say, the velocity of fluid flowing in the vicinity of that curve? Now there's no forces involved. If there's no forces involved, the line integral can't represent work. There isn't any work because there isn't any force. Well, what on earth does a line integral represent if the integrand is representing a fluid flow? And the answer is a little bit unsatisfying because it's not something that we have a pre-existing name for. And so I'm going to have to kind of segue into this, and it's a little bit of a weird discussion. But here we go. If we have a curve, oriented curve, and now imagine an area, sort of a cross-section area like that, and then imagine sort of dragging that area along the curve, and we have let's see, altogether, we would have this real weird, I'm going to say tube, but this is not an enclosed tube. This is just kind of tube-shaped collection of fluid there. And so what we're interested in, the question I'm going to ask, given that curve, given that area, looking at this fluid in green, that fluid is flowing to some extent along the curve and to some extent not along the curve. And I would like to know what is the combined extent to which that fluid is flowing along the curve. So in particular, each little piece of fluid, there's a little piece of my fluid that we're interested in. Again, what a weird question. Let me recognize, right? But we've got this amount of fluid. It's easy to write down how much fluid each little piece is. That's how much fluid we have. And again, the velocity, whatever the velocity is, who knows? The velocity might be like that. But if you're interested in the extent to which it flows along the curve, it's the component of that velocity in the tangent direction. That's the extent to which that piece of fluid is flowing along the curve. Right? So you write that down. Why are we interested in this thing? Not at all clear. Right? We're just trying to make sense out of a seemingly random question. But check it out what happens if you take all of that and keeping in mind we're interested in how much this fluid is flowing along the curve, and you write that down, etc., etc., And what you notice is that my answer involves, among other things, that vector line integral. And so there's an opportunity to make an interpretation here, and here's how I'm going to do it. I'm going to first observe that the answer also involves a factor of A, wrong color, factor of A, this area. And I'm going to say, of course it does. Silly observation, but as if you think about bigger areas would give you more fluid. And if there's more fluid, of course there's more fluid flowing along the curve. The fact that this is proportional to area, I'm going to say, is clear. That's obvious. So what we're going to ask instead, I'm going to redo the question, and I'm going to say per section area. Of course, this section area is proportional to the what we're computing. Per unit area, how much does the fluid flow along the curve? And per unit area, the answer is the line integral. So this is an interpretation we'll pick up from here next time and try to make more sense out of that. See y'all later. Have a good one.